In the last video we put together a massive breadboard which we'll start using today. I tried it out and those center power rails just get in the way, so I moved them to the edge. In this video we'll breadboard enough stuff to get at least something on the screen. At minimum we'll need the oscillator and clock divider, the video counters, and the video output section. After that we'll put up something simple like the borders. We'll start by building the oscillator. We'll need a 14.318 MHz crystal, the 7404 hex inverter in EZ1, and a few passives. This oscillator is straightforward with a very common design. You'll see these in most Atari stuff, other arcade games, and even the early Apples. In theory, the crystal is an RCL network fighting between charge storage and discharge at a resonant frequency. It also abuses the linear region of the bipolar inverters to amplify the changes, so I'm not sure if this design would work in CMOS. I'm too lazy to try it, someone let me know. Most crystals are parallel resonant, so this happy little cap here just assures there's enough series capacitance to start and maintain oscillations, and many designs don't have it. No, I'm no oscillator expert.
Oh man, I only ride them. I don't know what makes them work.
If you are an expert, we would appreciate a real explanation in the comments. Now, why such a strange frequency? Well, these are cheap and ubiquitous, but more importantly, you can derive most of the standard video timings from this. For example, the well-known color burst frequency is our oscillator divided by 4. Now, this game doesn't use color, but if present in a composite signal, colors in the video part are determined by a phase shift from the color burst reference frequency. Another timing example is that a single horizontal line takes exactly 910 of our oscillator cycles. The NTSC spec shows this as 2 times the color burst frequency divided by 455, which is about 15.73 kilohertz. 455 is half of our crystal's 910 cycles per line, so this makes perfect sense. And we'll see more of this timing later. Let's fire this up and take a quick look. Pretty much what we expected. Bypass that happy little cap. It's still running, but we'll leave that in. Let's build the oscillator divider. We'll need a 4-bit binary counter and FOX1. And remember, we're using pin-compatible 74161s. And the 7437 quad NAND buffer and Henry one. The 7437 is just a buffered version of a 7400, but since we're only driving 9 inputs, you can just use a 7400 and don't really need to buy and stock this unusual part. For low-powered Schottky, outputs drive 10 loads, and inputs only consume a half a load, so we should have plenty of room. Oscillators typically go through a buffer, but since it only goes to one input, there's no need here. This counter is configured to reload to 2 after hitting 15, so basically it's an offset modulo 14 counter. The system clock is then derived by ANDing the first 2 counter output stages. Usually for a particular system, when we're discussing the clock, it's the same frequency as the oscillator. But since the clock line here is a down conversion of our oscillator, I'll do my best to use concise language for each line for clarity. Now if you draw out what the clock signal should look like, you'll see an unbalanced pattern. If we didn't reload the counter, you would have a nice balanced 4 clock pulses for every 16 oscillator cycles. But with the reload to 2, we get 4 clock pulses every 14 oscillator cycles. Our clock is basically the oscillator divided by 3.5. Now I know you're thinking the same thing I'm thinking. 3.5? Holy divisor! But I know exactly what Wozniak was thinking, and I'll tell you in a bit. No Grok, a little younger. Nice! Let's fire this up, take a look. I'll trigger on the load line and it's pretty much what we expected. Let's build the horizontal chain. We just need another 2 counters and Love 1 and King 1. Now most sync counters of this era use 9 bits per chain and really try to keep the timings perfect. They first divide the oscillator by 2, run that into 2 4-bit chips, then into a single flip-flop stage to get the 9th bit. Remember that if we divide the oscillator by 2, we'll need 455 ticks for a single horizontal line. You can't get that with 8 bits, hence the 9th. Most designs then check for the counter to hit around 455 and reset to 0. To keep the chip count as low as possible, Wozniak was thinking, I only want to use 2 horizontal counter chips, so to spread those 910 oscillator cycles over 8 bits gives us about 3.55 cycles per clock step. Simple. I'll just divide the clock by 3.5 to get a good enough horizontal step clock. The line rate will be a little high, but close enough. Last time I checked, there were no NTSC police inside these monitors. Just need to get close enough. So I think that was his impetus behind our funky divided by 3 circuit. If you asked me to divide the oscillator by 3.5, I'd be staring at the wall for a while. These chips are drawn backwards compared to how you would count, so the lowest order bit is on the left and high order on the right. You can see that the clock line goes to all counters at the same time. These chips are synchronous and only step when both CE inputs are high. The terminal count pin turns on when the output is all ones. So the TC output from one counter is used to enable clocking in the next downstream chip, hence the term chain. Out the right end of this high order chip we get the S clock signal. Just like the low order chip, the TC pin rises when the counter hits all ones and stays high until it rolls over to 0. This will take 16 steps of the lower counter, so this S clock line will go high for about 3.9 microseconds. They use the S clock line to generate the H-sync signal, which in the NTSC spec is 4.7 microseconds wide. Evidently close enough to be detected by the monitor's sync separator. If we check the scope, we can see that the period and width match our calculations of 15.98 kilohertz and 3.9 microseconds, respectively. One quick note, you already noticed that the low order counter is loaded to 5 at some point. This is done once every frame, so not a general concern with horizontal timing. We'll talk about this in a bit. Also, we know our clock line is not real pretty, and if we draw out a few stages of this counter, we can see that the clock imbalance cleans up after passing through 2 stages of the horizontal counter. Both 1 Henry prime and 2 Henry prime have a 75% duty cycle, then 4 Henry prime is perfectly symmetrical. We'll see an interesting artifact of this imbalance when we get to the brick section. Let's build a vertical chain. We'll need 2 more counters in Mary 1 and Nancy 1, the 7408 quad AND gate in Henry 2, the 7411 triple AND gate in Nancy 4, and the 74175 quad JK flip-flop in Jack 1. The vertical counters step once every horizontal line via S clock. When a high order vertical counter reaches 1110, it raises this line, causing the loading of new values into the low order counters of both chains. You'll notice that the high order counters are never loaded and maintain their state. If we diagram this out, when the counters roll to easy 000, this line goes high. Well, we'll call it V-gate because it generates V-sync. Since V-sync is initially high, the vertical trigger line drops, loading new values into low order chips of both counters on the rise of the next clock. V-sync also drops on the rise of the next clock, turning off vertical trigger. So vertical trigger is only on for 1 clock cycle. At this point, the counters end up at easy 405. The vertical counter basically skips forward 4 steps every frame, producing only 252 lines. V-gate will stay on until the counters roll over to 0. So V-sync will be on for 28 horizontal periods, or about 1,752 microseconds. The NTS spec for the horizontal blanking period is 1,334 microseconds, evidently close enough. NTSC also wants 262.5 lines per frame at about 59.94 Hertz. Breakout produces a flatter picture with only 252 lines per frame at over 63 Hertz. This seems pretty far off, but evidently works. Let's take a quick look at the vertical trigger and V-sync lines on the scope. In line with what we expect, the vertical trigger drops for 1 clock and V-sync drops for 1,752 microseconds at a 63.41 Hertz rate. Let's throw this on the analyzer and trigger on the fall of V-sync. Looks just like our diagram. The counters roll to EZ000, bringing up V-gate and dropping the vertical trigger line. On the next clock, the counters are loaded to EZ405, V-sync turns on, and vertical trigger turns off. V-gate drops when the counters hit 0, and V-sync turns off at the rise of the next clock. Fun stuff. A quick note here, we discussed the vertical counter skipping 4 lines every frame, but we also see that the horizontal counter also skips 4 steps every line. I know it went from 0 to 5, but it was supposed to step to 1, hence skipping 4 steps. My initial thought is that this +4 offset is needed here so we can get ball motion in multiple directions. The ball counters are basically copies of the sync counters, so loading the ball counters with lower or higher values than a +4 offset will cause the ball to move forward or backward or up or down at differing speeds, depending on the axis. We'll look at this in more detail later. Let's drop in the additional parts needed to generate the composite output. We'll need a 7432 quad OR gate in Dog 2, a 7402 quad NOR gate in EZ3, 7486 quad exclusive OR gate in EZ2, this switching diode, and some passives. We'll use the video jack of our new control board as well. It's easier to think of these 2 gates as a single triple input NOR. 8 Victor Prime, 16 Victor Prime, and V-sync must be off for this line to go high, and this causes an inversion of the H-sync signal. You can think of an exclusive OR gate as a signal inverter. Whatever signal is flowing into one input can be inverted simply by turning on the other input. If we diagram this out, we can see that 8 Victor Prime and 16 Victor Prime are low during the first part of V-sync. This causes H-sync to be inverted for 4 horizontal steps. I think there may be some glitching here where the inversions are turned off and on. The NTS spec is way more complex than this, but I'm assuming this first portion here is enough to trigger a vertical retrace. The sync separator inside the monitor does 2 things. It uses the horizontal sync portion of the composite signal to align its internal horizontal oscillator, and it detects this longer low portion of the composite signal to trigger a vertical retrace. With an AC coupled signal, you can't keep the level too high or too low for too long, so the serrations here are required to keep the signal balanced and also to keep the horizontal counter aligned. Vertical retrace is not some magical super fast return to the top as shown in many diagrams, but takes some time. There are still horizontal retraces happening during the vertical return, as you can see here. Another thing to discuss at this point is that there are no pixels in a CRT. There are lines, but there are no pixels. There's only a horizontal sweep at a certain rate and the monitor's ability to control the electron gun. External systems driving a CRT define what pixels are by breaking up the physical portion of each line into as many pieces as desired, as long as the monitor can handle it. That's why they have these test patterns. You can easily see where the monitor can only handle up to a certain rate of input changes. Then the lines start to blur together. Breakout divides up each line into 240 visible pieces to create its playfield. One more side note, most drawings of video screens show the visible area in the upper left corner and the sinks along the right and bottom edges. This is a valid, easy way to show memory mapped video systems where the visible area might start at 0 and sinks start at some higher counter values. In reality, the visible area of a picture is centered around the sinks, so it's better for us to look at it this way. And then it really doesn't matter what the explicit counter values are as long as we generate the video and sync signals properly. Let's look at the composite sync on the scope. We'll trigger on the fall of V-sync. Exactly what we expect. Inverted for 4 horizontal steps. And some switching noise from lines and gates not perfectly timed. Let's plug this into a monitor. Well, it thinks there's a video signal. Unfortunately, this monitor doesn't show any detailed information about the inbound signal. I guess we'll just need to keep building. Let's drop in the additional parts needed to generate the borders. We'll start with just the top boundary. These signals here are the non-prime versions coming off the flip screen logic. So we'll just use the prime versions today because we still need to add that flip stuff. I'm going to use temporary jumpers for any counter lines then. We'll need a 7427 333 input NOR gate in Henry 3, 7411 333 input AND gate in Love 4, 7408 quad AND gate in King 4, 7400 quad NAND gate in Henry 4, and another 330 ohm resistor. While we're wiring that up, I built this diagram in Visio to help us plot out the screen. I started square, then shrunk the height by 25% to get a more realistic 4:3 aspect ratio. You can see the counters on each axis, and I left out the lowest order bits because they just don't fit. So the top boundary is visible when 128 Henry, 64 Henry, and 32 Henry are low, and 16 Henry and 8 Henry are high, and V-sync is not on. So we should get a vertical bar here. Let's tie these unused inputs and turn this on. Looks like what we expected. Let's wire up the left and right sides. We'll need another 7411 333 input AND gate in Nancy 4, a 7404 hex inverter in Jack 2, a 7402 quad NOR gate in Jack 3, these 2 switching diodes, and a pull-up resistor. If we plot this out, we can see that this looks kooky. The left-hand side is okay, but the right-hand side is left of left. Never a good thing. If you remember, the vertical sync is from EZ4 to 00. So let's shift the vertical axis a bit to center this plot on the sync. Much better. Let's fire this up, take a look. Not too exciting, but we needed to get through a lot of stuff to get here, so it was a long session. Ah, crap. I thought we were done for today, but in the project plan I said we're going to input schematics as we go, so let's just get her done. We're going to make the retro schematics look like the originals as much as possible within reason, so some of our library symbols will need to be custom. We'll create a 74161 like in the legacy schematics. The 74175 is pretty close. We'll copy that and make some adjustments. I'll copy other standard gates as well and make adjustments as I see fit. It's finally time to create a retro project, and we'll start by adding all the parts we used today. Let's draw the oscillator and clock divider. Let's draw the horizontal and vertical video chains. Let's draw the sink and output section. Let's draw the border logic, starting with the top boundary. Add in the left and right sides. Adjust all the labels. We'll rename the sites properly. I thought I'd need all gates in a package to get the gate sequencing right, but I see now that you can make any adjustments you need. I'm still learning. I'll kill off this flotsam. Looks okay for now. We'll start the board after we get a little further along. I think that's enough for today. In the next video, we'll need to add in that flip logic before building too much other stuff. And we'll add something more exciting like at least the paddle. Thanks for watching.